Hello everyone and welcome to another section of our deep dive series. Today we're going to be talking about Elasticsearch, which is one of the most popular and powerful open source distributed search engines. Reminder that our deep dive series is intended to give you depth that's going to be relevant for your interviews. And so what we're going to be trying to cover here are both how technologies can be used in an interview in an assistant design setting, as well as how they work so that you can understand the internals and answer questions that may come up. I'm Stefan. I am one of the co-founders of Hello Interview. I've worked as a senior manager at both Meta and Amazon, and over the course of my career conducted north of 2,000 interviews. Very familiar with how interviewers tend to think about the process and hoping to share some of those insights along the way. This session is going to be divided into two parts. In the first part, we're going to talk about how to use Elasticsearch. This is particularly relevant for interviews where search is actually not the primary functionality, or in certain types of interview, like the product design interview at Meta, or interviews for full stack engineers at startups, where your interviewer wants to see you solve problems, not necessarily you have deep knowledge of how distributed systems work. In the second half of the session, what we're going to do is peel back the layers of Elasticsearch and talk about some of the design decisions under the covers and how clusters function. The goal there is both to give you some insights into how it actually functions, but also some inspiration for your own designs, especially as they pertain to more infra-style interviews. Before we get too deep, just a reminder that all of this information is available on our website, hellointerview.com. There we've collected a bunch of deep dives on technologies that we really think you should know, just like Elasticsearch, as well as common problems that you might encounter in a system design interview. In these instances, we've broken it down, walked through some of the different choices that you might need to make, and then giving you an indication as to which ones are great and which ones are probably not the ones that you might want to use in an interview. We've also recently launched our Guided Practice product. Guided Practice is solving this problem that a lot of people watch videos, they read blogs, and they kind of fail to integrate the information that they've consumed. With Guided Practice, you're actually going to work through a problem. You'll submit your answers on a whiteboard by narrating your response, and then you'll get personalized feedback on how you did, what things went well, what didn't go well, and how to improve. This is a great way to make sure that you're actually retaining the information that you're taking in, and there actually is a guided practice for post-search, which is a perfect complement to this video. In the first half of this video, we're going to talk about how to use Elasticsearch in a system design setting. For that, we first need to talk about search. So what is search? Well, typical search experiences are comprised of a few different pieces. First, I'm going to give the search some criteria. Let's pretend that I'm searching for books. I'm actually going to use a bookstore as a motivating example throughout this video. So maybe I want to search my bookstore for books that have the title that contains great and for a price that's less than $13. That's potentially describing a lot of books. So I might want to sort those books in my search results. In that case, I might specify that I want to see the most recently published books that contain the word great. In my search result page, I might also have an option to break down the search and refine what I've described. These are typically called facets or faceted search. And one example is I might want to refine by the publisher, maybe Hachette or Simon & Schuster. Boo Hachette for suing the Internet Archive. Anyway, the net of a search experience is a set of results, basically a set of documents. In this case, the documents represent books that I want to return, but they could really be anything. We can think of this as arbitrary JSON blobs that we might want to return. While Elasticsearch does support other use cases like analytics use cases as part of the ELK stack, I'm not going to talk about this too intensively in this session just because search is really rich and I want to go into more detail. Now, how does Elasticsearch think about search? Well, there are some key concepts that we have to identify and name before we can go into more detail about that. The first and most important concept is the document. Like I mentioned, documents aren't necessarily PDFs or things like that. They're just JSON blobs, and they can potentially contain anything. The next primitive that we're working with in Elasticsearch is called an index. And index is kind of an overloaded term. In computer science, index is usually referring to how we structure data to make retrieval really fast. In this case, an index is just a collection of documents that we want to make searchable. Within an index, we have two relevant concepts. One is called a mapping and one is called a field. The mapping is going to specify, in some sense, the schema that I want to be searchable on my documents. So my documents might have dozens of fields, but my users may not need to search all of those. My mapping, in some sense, is telling the search engine, Elasticsearch, which of those fields are pertinent, and then what are their types. So in this case, I can tell Elasticsearch that the price is always going to be a floating point number, and as a result, Elasticsearch can organize that information so that I can have range queries and I can find price less than $13. So with our terms in place, we can now talk about how we actually bring docs into Elasticsearch and how we make them searchable. Elasticsearch provides a RESTful API, and it actually has a pretty good one. So if you haven't designed a RESTful API before, it's actually a useful one to look at, both so you can get some ideas about what a solid production level API looks like and how they handle some complicated corner cases. The very first call that we're going to make is this put to / whatever our index name. So this is creating a books index. And I can specify some configuration parameters, but all of them are optional. I'll get into what shards and replicas are a little bit later. Important thing here is this creates me an index. I don't have to specify a mapping, but I can. And the reason that I might want to is because if Elasticsearch can't infer the types of the fields, which ones I want to search, particularly complex configurations, it may make some mistakes. There's also a lot of overhead to having Elasticsearch guess at what your mapping might look like, because it's going to be indexing a bunch of fields that you may not care about. Now note the field types here have a ton of implications. We talked about how the price we wanted to be able to do range search on, so that's available here. Note also that we've got these text and keyword types. Text allow us to do rich full text search. So if I want to search for great in Great Gatsby, I can do that in a text field. A keyword, on the other hand, is opaque. Each of the tokens is kind of a unit. And so this is really appropriate for places where, for instance, my set of categories is fixed, maybe in the UI, and the users can click or select from the available categories. This guarantees that I can do those lookups lightning fast, think a hash lookup, but it won't allow me to, for instance, search for all categories that contain the word fiction when that might include nonfiction. Note also here that I am including this nested reviews. This, if you're familiar with normalization and denormalization, might be a little bit clear, but what we'd like to be able to do is answer our search queries with as few requests as possible. And by nesting the reviews in the document, we can basically construct queries where we can say, I want specific types of books that have certain reviews. Now this is not without its downsides. If reviews are changing a lot, or if my queries rarely touch them, this is actually going to be really expensive for me to maintain that way, and I might actually be better served by creating a separate index for them. But in this case, I'm showing you what this might look like and assuming that reviews aren't going to be shifting a lot, but that customers care about them. Next, let's talk about adding documents to our index. This is dead simple. I make a post request to this _doc endpoint inside my index, and I pass all of the document's contents. When I do this, Elasticsearch is going to respond with a basically success message that tells me a number of details. For instance, what was this document's identifier, what was the index it was created into, and this version number. The important thing here is that Elasticsearch is a distributed system. We could be making updates from any node, and they might take some time to percolate through the system. So it's really important that we handle collisions and concurrency. This is particularly relevant when we start to talk about updates. For updates, the simplest possible API is to make a put request to this doc endpoint with the ID that I'd seen earlier. I pass in the entire document body and I can update it. Now, this is probably overkill if I just want to change the rating on one of the reviews, for instance, but it also has some downsides in that if two updates are submitted simultaneously, the last one wins. This is where that version identifier comes in. What I can do is in my update, I can pass in the version number. And what Elasticsearch will do is it will reject that update if that version number doesn't match. This gives me a chance to handle the collision or the conflict on the client. My client can then go and query what the latest version is, take a diff, decide what to do, and resubmit its request. This is actually a pretty common pattern in distributed systems, and it's just a way to ensure that the update happening is the one that we would anticipate. Another strategy here, which actually doesn't solve the race conditions, but solves part of the problem, is that I can make field-by-field updates by posting to this underscore update endpoint. And in this case, I'm simply bumping the price from $13.99 to $14.99. Okay, so we've talked a lot about how to insert and update documents as if Elasticsearch is a document database, and it kind of is, but the key thing here that we want to get into is search. Well, fortunately, search is really straightforward too. There is this nice API endpoint underscore search, which sits on the index and allows you to search using this query language that's basically JSON and very SQL-like in nature. So if, for instance, we wanted to allow searches by title where it contains a specific word, then we can just simply do a match query with great in the body. If we wanted to extend that by saying that we also want it to be less than $15, we can do that. And then if we wanted to have a query of books where the reviews had this comment excellent and their rating is greater than or equal to 4 out of 5, we can do that too. Now note these are GET endpoints. You can't actually put this in the body of a GET request. It doesn't actually meet standards, or you can actually stuff this into a query parameter, but you're limited by the size of a URL, which I think is 2048. Someone in the comments, please correct me. It's also possible to post here, although that's a little bit out of canon in that most of the time when you're doing search requests, you're expecting them to GET. They're not actually mutating anything. But the important thing here is this API is really nice and convenient and allows you to specify arbitrary search criteria, the first part of the search product that we talked about earlier. Now, once I've got search results, they're going to come back to me in an API that looks like this. Elasticsearch is going to conveniently report to me how long that search took, whether it timed out, how many shards it hit. Again, we're going to talk about this a little later. And then it's going to tell me how many hits. And it's going to return the contents of those documents to me. Now, this is configurable, and in some sense, you may not want to return the entire document in your search results, but Elasticsearch has this underscore source, which is basically that source document that you originally uploaded. It's also possible to return only specific fields from the document. I may only want the ID or the title. I'm always going to get the document ID inside of Elasticsearch. There's also this field called score, which is trying to calculate the relevance of the document to the query that I've input. And that brings us to the second part of our search product, which is the sorting. Just like searching and filtering, Elasticsearch has a pretty extensive API to allow you to specify whatever sort order you want. So in this first instance, I'm sorting exclusively by price. Whereas in the second instance, I'm sorting first by price and then by publish date. Remember that I need one field to be the first and most important sort order. The remaining fields are basically tiebreakers. I can also specify scripts. Elasticsearch has a language they call painless, which allows me to specify basically formulas that I can use to calculate. So this would be the price with a 10% discount. Doesn't make any sense as a sort order, to be frank, because the sort doesn't actually change, but you get the general idea that you can pass in a formula here. I can also sort by those nested objects and fields. So if I wanted to sort by the highest review, I could do that as well. Elasticsearch will allow me to specify the sort order very rigidly. If I want to, I can tell it exactly which fields to order on. Or I can use that underscore score field that we talked about in the result set earlier, which basically orders by relevance. Now, relevance is a really deep topic. There's some machine learning and statistics aspects to this, but some of the simplest algorithms are actually pretty intuitive and easy to understand. So the most simplest of them all is one called TF-IDF, Term Frequency Inverse Document Frequency. And there's two fundamental observations here. First, the most relevant document probably contains my term more frequently. If I'm searching for Elasticsearch, I want it to mention Elasticsearch a lot. The second thing is I'm going to favor those words that don't appear very frequently across all my documents. So as an example, if I'm searching for Elasticsearch Guide and I've got two documents, one is a short document, which is functionally an Elasticsearch guide, and then the second is a summary of a court case about some weapon being handed to a guide and the prosecutor using the technology. Which one should I prefer? They both contain Elasticsearch and guide. Well, the first term frequency is going to tell me that Elasticsearch appears very commonly in this document. So it's going to get a score boost just by the number of times that Elasticsearch appears. The next thing we're going to note is that guide actually appears in a lot of documents. It not only appears in my Elasticsearch guide, it appears in court cases, it might appear in a birdwatching guide, and as a result, it's a relatively uninformative term. So what TF-IDF is going to do is it's going to score those items which contain the keywords that are densest and don't appear in many other places higher than those keywords that maybe don't appear very often or appear in almost all of the rest of the documents in my corpus. The default scoring algorithm is not actually TF-IDF, but it's a close variant and it's a good enough approximation. You can assume that Elasticsearch is basically making some statistical inferences based on your documents if you don't specify a specific sort order. Now that we've filtered and sorted the results, we're almost ready to send them to the user, but we've got one last step, which is we might have millions of results that we could potentially return, and most people aren't going to scroll to actually see all of them. It'd be madly inefficient. So we need to institute some sort of pagination. There are two types of pagination, stateful and stateless. Stateful pagination requires that the server keep track of something, so that way it knows what the next page is. Usually you're talking about cursors here. In stateless pagination, we're going to pass in some sort of parameter that allows us to localize approximately where in a result set we'd like to look. So as an example, this from and size query is simply going to take results starting with the index of from, 0, and pages of size 10. It's going to take the first 10 results and return them to me. When I query again for the next page, I'm going to increment that from to 10. I'm going to keep the size the same, and that will give me the next 10 for a total of 20. Very straightforward. I can also use this search after. So in this case, I'm sorting by date and ID. When I get to the bottom of my results, I am going to have a date after which there are no more results in subsequent pages, and an ID after which there's no more results. What this is telling Elasticsearch is it's saying, don't return me any results that might be before these two quantities. These are both comparable, but search after is preferable, particularly in the cases where you want to go deep into the pagination, because this requires that me get all the results, and then we're going to slice into that result set based on the inputs, whereas this actually allows me to restrict the documents that I'm querying based on this search after. After I've gone deep into the result set, I may actually have a much smaller corpus of things that I can search over, and so Elasticsearch has to do less work. It's a kind of clever idea. Now, both of those search types have a problem, which is the index is constantly changing. New documents are being added, some are being deleted. In the worst case scenario, you actually have a document which would have been on the next page, but changed, maybe due to a deletion, and bumped up to the page that you were just on. If that's the case, then your pagination, whether you choose search after or the from and size, is going to miss a document. So how do we deal with this? Elasticsearch supports a point-in-time search. And the idea here is I can create a point in time where Elasticsearch is going to snapshot what the index looks like at that period. This is going to return me an ID, in this case 46T0. and I can use that point in time while I'm searching. Note I need to specify a keep alive. This is actually pretty expensive to maintain, and so I need to signal to the server that I still want it for 1 more minute every time I search. But what this does is it searches based on that snapshot and will guarantee that each page of results is consistent. When I'm done, I need to delete that point in time or let it expire so that I'm not using excess memory on the server. But this eliminates at least a small class of problems that you might have with respect to pagination. How this point in time is implemented is an interesting point of discussion for the next section of our video. Before we move on, I want to briefly summarize how you can use Elasticsearch in your system design interview. Typically, Elasticsearch is going to be for complex search scenarios. If you need to do geospatial indexes, if you need to do vector search, if you need to do simple full text search like we've described, Elasticsearch is probably your friend. It doesn't necessarily mean that Elasticsearch applies in every scenario, and there are some potential potholes that you need to be aware of. First of all, Elasticsearch is probably not going to be your primary database. While the API that I described looks a lot like a typical document database, Elasticsearch's durability and availability guarantees aren't actually that good, and over time, most people have relied on setting up a primary data source, be it Postgres or DynamoDB, and then using change data capture, CDC, to basically push updates from that database into Elasticsearch. The idea here is Elasticsearch is going to be a little bit behind your database, but it will have all the updates. The next thing is Elasticsearch is going to work best with read-heavy workloads. If you've got a lot of writes happening, or if your writes dominate your reads, you may want to consider whether Elasticsearch is appropriate. There's a lot of ways that you can change the nature of your workload, maybe limit the number of writes or batch them out, but generally speaking, Elasticsearch is going to perform best when we're reading a lot of data. If you're using Elasticsearch, you have to be able to tolerate eventual consistency. It's going to have a delayed version of the data. Eventual consistency is basically endemic to the design of Elasticsearch. If you need strong consistency, if you need to check for double bookings or things along those lines, you're going to need to use a different database. But if you're not using it as your primary database, you already know that. Denormalization is really key to making Elasticsearch functional. If you've got a particular search page, make sure that you flatten all of your data and that you're not trying to make nested relational queries. You basically shouldn't need to do joins in an Elasticsearch search. If you do, you're going to be in trouble. First of all, because joins aren't supported, and secondly, the way that you might bolt on joins by doing lookups outside of Elasticsearch is really going to compromise performance. And the last thing to consider before you use Elasticsearch is whether you actually need it. Elasticsearch clusters are not a trivial matter to operate and maintain. It's a new technology. In a lot of cases, a simple search capability in your existing database might cover your needs. If you need full text search, if you need to index billions of documents, Elasticsearch is your best friend. But if you've got simplistic needs, aim for simple solutions. You don't necessarily need to dig in. So far, we've talked about Elasticsearch primarily from the angle of a user or a client. And from an interview perspective, this is still incredibly useful. In a lot of interviews, what you need to be able to do is to point out when you might use Elasticsearch and how it might fit into your overall design. If you're designing Twitter, search might be a peripheral concern for your overall design, and delegating that to Elasticsearch is a completely sensible design choice. In other interviews, either because your interviewer explicitly tells you, don't use Elasticsearch, I'd love to see how you implement some of the core concepts, or because they tell you to implement a system which seems a lot like Elasticsearch, being able to understand what goes on beneath the covers of Elasticsearch is going to be helpful, and that's really what this second section is about. Now, the first thing that you need to understand about Elasticsearch is that it is, in some sense, an orchestration layer for Apache Lucene, which is a low-level search functionality. Elasticsearch handles the distributed systems aspects, the API, how to manage nodes, how to manage backups, how to keep availability and replication, whereas Lucene is trying to make sure that the data is organized and that it's fast. Lucene operates on a single node. Elasticsearch operates at a cluster level. And so as we're peeling back the onion of Elasticsearch, we're going to be progressively talking about the different layers inside of Elasticsearch before we talk about some of the fundamentals of Lucene. The first thing to understand about Elasticsearch as we kind of peel back the layers of the onion is the various nodes that make up a cluster. Now, an Elasticsearch cluster can have a single host or server. Node is not necessarily a physical machine. And a physical machine can take on the responsibilities of multiple nodes. But at a conceptual level, these are the responsibilities that exist inside the Elasticsearch cluster that need to be performed by some hardware somewhere. The first node type is our master node, or our master eligible node. And what happens here is when we spin up our cluster, we are actually specifying seed nodes or seed hosts, which Elasticsearch will try to connect to, and then will elect a master of the cluster. We only want one master node so it can make administrative decisions like when we create indexes or which nodes are actually part of the cluster. But the important thing about master eligible nodes is that there is only one master that is elected at any point in time. The next node type is the coordinating node, and you can think of this as kind of the API layer to the cluster. The vast majority of requests that are coming into my Elasticsearch cluster are going to be search requests. And what coordinating nodes are doing are they're taking those requests, parsing them, and then passing them to the relevant nodes that have the data that we need in order to return the search results. Users are, for the most part, interacting with these coordinating nodes. Data nodes are where our indexes are stored. They are functionally where we keep our documents, and they're probably the most fundamental of all the node types. We're going to have a lot of them. Data nodes need to have really heavy I/O, either lots of memory or plenty of fast disk, because the coordinating nodes are going to be sending search requests and they expect the data nodes to be able to respond. The ingest nodes are like the backend for our service. That's how the documents make their way into the cluster. And finally, the machine learning nodes are not always used, but are for machine learning intensive tasks. And the idea with the machine learning node is these nodes might require access to a GPU and are going to have very different access patterns. Now, each of these node types, by virtue of their responsibilities, actually imply different hardware. My master nodes need to be incredibly robust and reliable. It's very important to me that they're not going down. My coordinating nodes are going to do a lot of network traffic with the outside world. My data nodes, as I mentioned, are actually going to have a lot of disk I/O or need lots of memory. And my ingest nodes are going to do a bunch of analysis of documents. They typically are more CPU bound. And so what this implies is when I set up a cluster, I might actually choose different server or VM types to take on these node responsibilities in order to optimize my cluster. Remember that the fundamental grouping of Elasticsearch documents is an index. This might be my books index or my reviews index. Inside of an index, I actually have shards and replicas. And these shards are actually going to be responsible for both containing all of my documents, but also building up index data structures to make searching fast. The shards are mutually exclusive. If I've got a document, it will be assigned to one shard or another. And the replicas are basically going to be carbon copies of those shards. I might have, for instance, a replica of a shard across multiple machines. And what this allows me to do is when I'm searching, my coordinating node can choose whether it wants to use shard 1B or shard 1A and spread the load across them. So by replicating these shards, I actually gain throughput, particularly on the read side. By sharding, I can spread out very large indexes across many different machines. I believe a shard has a hard limit of 2 billion documents, which is a whole lot, but even if I've got a smaller number than that, I still may want to divide those documents either because the aggregate size is too large for a single machine or because I want to spread the load across my cluster to make my queries faster. This is the central idea of Elasticsearch, is that these shards are breaking down my data, and inside of each shard is this Lucene index. The Lucene indexes are one-to-one with Elasticsearch shards. Basically, a shard is just encapsulating a Lucene index. Inside Lucene index, we have segments. And the way that Lucene works is basically by accumulating these immutable segments. What happens when I create a new document is Lucene will first try to batch that document into as many writes as it can contain before flushing it out to create a segment with multiple documents. When I add more documents later, I might create a new segment. And then at some point in the future, Lucene may decide that it will merge these segments into a third segment and then delete the old ones. The important thing is that these segments are immutable. They're not changing. Now, we support updates in Elasticsearch. How does that actually work from a Lucene perspective? Well, with updates, what we're doing is a soft delete. So Lucene inside these segments maintains a map of deleted documents. So if segment 2 contained document 1, 2, and 3, and I deleted document 2, this segment will actually store that identifier 2 internally, and then when I query that segment, I will remove any results that contain 2. It's been deleted. When I do an update, what I'm going to do is soft delete. I'm going to mark that document as deleted in the old segment, and then create the updated document in a new segment. This maintains this immutability. Aside from that map of deleted documents, these segments aren't changing. And it's one of Lucene's more powerful features because it enables us to exploit a bunch of caching and concurrency benefits. Since segments aren't necessarily changing, when I load them from memory, I can do that in a compressed format, and I can load them all at once. I can guarantee that they aren't changing underneath me. I also can have multiple readers touching the data in the segment in a concurrent way without worrying about race conditions or contamination. The segment data won't change. It's read-only in some respects. And so this Lucene ideal of maintaining these immutable segments is really key to both the performance of Elasticsearch. It allows it to be very fast, but it also puts some limitations that we discussed earlier on being more read-heavy and not being able to deal with updates or insertions as quickly as maybe other systems that might allow immutable data. Inside the Lucene segments, we need to store all of our documents. Conceptually, you can think of a segment like containing documents, but the important thing is that those searches need to be fast. It's not enough to just dumbly store our data in these segments. We need to make sure that we can search quickly. Lucene employs several techniques in order to pull this off. One of them is a reverse or inverted index. Let's talk about that briefly. So when you want to make things fast with computers, you've kind of got two options. First, you can consider how you arrange the data in memory. If you store an array randomly, you may need to scan over the entire array in order to get the thing that you're looking for. If you sort it, you can find an element in log n time. If you know exactly what you're looking for, if you want to do a lookup, you can do that in O of 1 time with a hash table. So changing how you organize the data is one key. The next key is being able to use copies. If we can make a copy of our data and store it in a slightly different way, then we can potentially make access to all of the data really fast. Now, of course, we trade off storage. There's a bunch of costs that are associated with it, but those are really the two options for how we can make systems fast. So that very first data structure, this inverted index, is basically making both those trade-offs. What we're doing here is we've got a set of documents. The first one says lazy dog, it's ID number 12. And then the second is ID 53, and it says lazy days are the best day. In my index, what I'm going to do is store a dictionary of the words that are in the documents to the identifiers of each document that contain them. And what this will allow me to do is I can very quickly, in this index, look at all documents, I can look at all documents that contain the word lazy. I simply go to the lazy index. I can do that with a hash lookup, and then I can grab all of the documents that it contains. Now, there's a bunch of complexity that comes into these indexes. For instance, I might have variants of lazy that I want to be able to include. I might have other ways of spelling dog that I want to collapse together. And certain words like R may appear in almost all documents, and so maybe we don't want to include them. This is fundamentally a question of tokenization or stemming or lemmatization, and we won't go into too much detail about this, but this is an important consideration in order to make these indexes quick. Now, my inverted index gives me a series of document IDs, but my search query might actually have a sort order. Maybe I want to sort by price. How can I actually make sure that my results match that query? The next step for us is to think about how the data is actually arranged in memory. There's fundamentally two different ways that you can think about how to organize a table of information like what we have here. The first is what you would do in a SQL database. Each of these rows would be stored basically contiguously, and you would have a bunch of structs or fields that are going to represent each of these inputs. So as an example, this is a piece, this is a piece, and this is a piece. My table is an array of these rows. Now, this makes it really easy for me to get the entirety of a row given an identifier. So if I know what my ID is and I can look up the row index, then I can very quickly pull all of the data for that record. And in SQL databases, this is a very common operation. But what we want to do in this case with our Lucene segment is we want to take a bunch of doc IDs and resolve one of the fields. We, for instance, want just the price. We may not even care about the title and the author in our query. And so in this case, what we want to consider is a columnar store. In this case, we're actually going to store the data as a bunch of columns that we then concatenate together. So instead of thinking of the table as rows that are sitting on top of each other, we'll think of it like fixed length columns. And what this allows us to do is it allows us to get a single or a small number of field values across all of the documents very quickly. If I have a large number of doc IDs, I can grab all of their prices without iterating and crawling over the entire table, grabbing each row, even though I don't care about title and author. In Lucene, this is an index called doc values, and doc values contains these columnar fields that allow it to do very quick sorting and filtering based on those doc IDs that are identified by the inverted index. Now, while Lucene has some very low-level optimizations for how data is organized to make the queries as fast as possible, there are also other optimization opportunities that exist inside of Elasticsearch. One example of this happens in the coordination nodes. When a query is received by a coordination node, it is first parsed, and then there's an opportunity to optimize that query. What happens is the system will basically plan what data it needs to access in order to get the results the user wants, and try to optimize that plan in order to make it as efficient as possible. Now, what might be efficient or inefficient? Let's pretend that we've got a query that has two keywords, bill and nigh. And in our index, we have 1 million documents that contain the word bill and 1,000 documents that contain the word nigh. There's a lot of different ways that we could execute this. Well, first of all, what we could do is we could grab all of the documents that match bill, all of the documents that match nigh, union them together, and then do a string search through all of their contents. This is clearly very slow, and it would give us the correct answer of all the documents that contain bill and nigh together, but it would require that we transfer the entire content of the document across the network, which is just a non-starter. Another option is for us to use these IDs. So we could go and query all of the documents that contain the ID for bill, and we could intersect that with all of the IDs for nigh. Now this number is necessarily less than 1,000, so a lot of these IDs aren't going to match, but the IDs that have both Bill and Nye are going to be matches to our query. That sounds pretty good. But we can do even better than this. For instance, if we start with Nye, we don't have to transfer 1,000,000 document IDs over the network. We only have to transfer 1,000 document IDs over the network. And we might be able to do even better by finding all of the documents that contain Nye, and then searching through their contents to see if any of them contain Bill. This is a much bigger number, and if the contents are small enough, we can simply do an aggressive search across a very small number of documents. So this is the essence of query planning, that there are a lot of different options that give the same result, but have very different performance characteristics that we get to choose from when we try to execute a query. And on the coordination nodes, we have this option to generate query plans, and then using statistics that we have on our index, like how many documents match a particular keyword, we can then go and decide which shards we want to access, which Lucene segments we need to go and query, and how we can get the results back to our users as fast as possible. All right, so we've gone super deep to understand how Lucene works at a low level to answer search queries, as well as optimizations that can happen on coordinating nodes to do query planning and optimize the execution plans. Let's take a step back to walk through the entire layer of the onion to talk about how documents are ingested into an Elasticsearch cluster and how they're made searchable. So the very first step is to create a document. In a typical setting, a client is going to send a document to an ingest node, which is going to run an ingestion pipeline and process that document before passing it along to a data node. Once that data node has received and indexed the node, it's going to send an acknowledgement back to the ingest node, which can be confirmed back to the client so they know, hey, my document's been received. On that data node, we are going to add that document to a Lucene index. In most cases, that's going to result in the creation of a new segment. If we've been adding a lot of other documents, there may be a buffer and a segment might be created with multiple documents. Now, when it comes time to search, our clients are going to contact the coordinating node. The coordinating nodes are going to parse the query that the user has submitted. They're going to make a plan for how they can access the data, basically which shards it resides on, and then they're going to submit those to the relevant data nodes. The data nodes are then going to pass that query to their Lucene indexes, which are going to run in parallel across the relevant segments and utilize features like the inverted index and the doc values to both filter and sort the results before returning it back up the stack. The data nodes are then going to return those partial results to the coordinating node, which merges those results and returns them back to the user. So we've got parallelism at multiple levels. We could potentially have multiple shards that are being queried. We could potentially be sending requests to different replicas. And inside the index, we can parallelize the operations across multiple CPUs. Thank you for sticking with me through this video. We've covered a ton of ground. If you've got a high-level interview coming up, either full stack or product architecture, I hope you can use Elasticsearch in those instances where you need high-performance search for complex scenarios that really require immense scale. If you've got an infrastructure-style interview coming up, I'm hoping that learning about Elasticsearch's internals and how Lucene works is informative and builds some inspiration for some future designs that you might have. I'm happy to answer any questions that you all might have in the comments and would love any reactions or ways that we can improve this. In general, we put out lots of great content on this channel, so subscribe to us if you're interested in more system design or more interview-specific content. And until next time, I'm Stefan. Talk to you later.